repurposing a bunch of systems on IP and stuff, wiping out flash. Talk to them.
I actually, the other day,
and in my day job, I work for a large Linux company. But I'm here today to talk about the Linux kernel and the portability of Linux from one system to another. Now, I'm coming at this from the point of view of someone who worked in the embedded space for a long time, so building little gadgets that run Linux. Some of these little gadgets are actually quite large, right? People use the word embedded to describe a lot of different things. I mean, I think one of the largest systems I worked on that was technically embedded was a very large magnet, right? We have a very small Linux system controlling a huge magnet. You could fit 3 of them in this room, perhaps, okay? So just because we say embedded does not mean it's small. So that's kind of where I'm coming at for this talk. There's a kind of emphasis on embedded systems, but most of this is relevant to a wide variety of different kinds of computer system on which you might run Linux. The key point being, I'm not really a big PC fan, so you won't see anything with an x86 chip here. That's just to kind of point out to you that Linux is more than just a PC running Linux. There's a lot more to it than that. As I go along, you can stop me at any point with questions, and I'll try to address them now. And if they're a longer question that requires a more in-depth discussion, then we can defer it to the end, or we can bring it up in the pub afterwards. That also works. Now, this is labeled Part 1. And the reason I labeled it Part 1 was very kind of pretentiously, because if this goes well as an overview introductory session, then I'd like to come back and actually have more of a hands-on session where we have, now I don't have one device for every person, but we'll have to work out the logistics. But it'd be fun to kind of have more of a hands-on session where we sit and actually, compile out the kernel for different devices and get Linux up and running on them. So that's what you came for. I'm sorry, we're not quite doing that today. We are going to talk about that kind of thing. We are going to address the issues, but we're not going to actually do a hands-on session. Not this time.
The next available spot in February.
Sorry?
So the next available opening for that would be February.
Okay. So if you guys enjoy it tonight, let us know, and I guess it's a threat as well, because even if you don't enjoy it, I might do it anyway. But shout if you hate it, and we'll try not to do it again. All right. So let me use this system here. Okay, so the obligatory biography about me. I'll keep it brief, but long-time Linux enthusiast. I've been using Linux since about 95, something like that. I was 13 at the time. Spent a lot of time doing embedded stuff. Moved here to do enterprise stuff over in Westford. In my spare time, I write articles, a couple of books. There's a couple of really good books coming out on Linux very soon, and you're going to want to buy them because they have a feature guide. This is on the cover. Okay, so look for a book with this. All right, you want to buy that.
You'll be autographing those the next.
Oh, sure, yeah, I can bring a few here. We can do, no, but yeah. So that's me. Okay, that's it. Next slide. That's enough. Okay, overview of today. So, Linux system architecture. Let's talk about what Linux systems are. Let's talk about the different components of a Linux system. Where does the kernel fit in? Where do libraries fit in? Where do applications fit in? How do they talk to each other? What is a Linux system? Keep that fairly brief. Introduce the Linux kernel itself. I'll do a very quick crash course in compiling a kernel, getting hold of it, and doing some development with it. A couple of example modules. Then we'll get into talking about the Linux kernel's portability. So if I have Linux now, and a new Wi-Fi router comes out like this one, and this is really cool. I bought a Buffalo one. If you guys saw Slashdot about 2 hours ago, you'll see a big story about these guys being sued over Wi-Fi. So that's an interesting little anecdote there. But new device comes out. I want to put Linux on it. So how do I do that? What's involved? So what does it mean to port the kernel? And what does it mean to build a complete system based upon that? So, you know, like, this is more than a Linux kernel. This is a Linux kernel plus a lot of other stuff that actually makes it do what you paid for, right? Because if it was just a Linux device, that would be cool, but a kernel on its own doesn't do very much. Not that you see anyway. And questions and answers. So if you have any questions, just stop me at any point, shout at me, get my attention, and we'll try to cover your questions as we go. So with that, let's get into Linux system architecture. Am I standing in the way? I think maybe if I... No? No, can you see?
No, it's fine.
Well, maybe I'll... Okay. Well,
Well, that actually is kind of around that. You can probably just unplug it and untwist it.
yeah. All right, gee.
Or run around the desk.
And do your partner.
There we go. Right.
Okay.
Let's do that, because then I can make sure you can all see, I hope. All right. Okay, so I'm not an artist. You probably noticed that already. I'm really sorry about some of my diagrams. They are atrocious, but bear with me. This is as bad as they get. This is kind of an idea, an overview of a complete Linux system. So at the bottom here, we have a Linux kernel, the core of the operating system. We've got these things here represent loadable modules, drivers, things that we can add to the system after it's been built and while it's running, okay? And then we have, this is kind of in a dotted box here because then we have these interfaces. We have these defined interfaces here by which the kernel communicates with the rest of the system, okay? Now, these are stable interfaces, okay? So if I have an application now written for a Linux system, and when I say Linux, I mean Linux running on anything, but let's, for the sake of argument, say I have a big PC-type machine that is running a piece of software now. That same piece of software, I want it to continue to work in 2, 3, 4, 5 years' time. And of course, we know that's true. We know that if we take an application from 5 years ago, possibly by installing some compatibility libraries or something like that, but in general, we can install the application and it will work just fine. And that's because we have these stable interfaces here, okay? So there's kind of an edict from on high. Don't break that, okay? Because people will complain. If applications don't work anymore, people notice very quickly, right? Anything else, you can, you know, sound driver doesn't work, 100 people get upset, you know, no problem. But you don't want to get everybody upset. So this is very, very important. The interface is very, very important. So then, built upon this, we have our C library. Okay, so I'm talking about regular applications here. I'm not going to kind of jump up the stack and go into the world of LAMP and web applications today. I'm talking about kind of old school stuff here. We have our C library. Okay, and the job of the C library is to take all of this gunk here and provide us with a nice set of APIs, a nice set of functions, things that our application can call to get stuff done and not have to ask the kernel directly. You know, we like to abstract stuff where we can. Okay, so that's why we have C language and the C library that comes alongside it. Now, sitting above the C library, we have our applications. So I install a program uses the C library asks the kernel to do stuff on our behalf. That's the defined order of things. Except for these things over here, these are kind of special case exceptions to the rule, things that, you know, we're not entirely sure how to classify them, things that ask the kernel to do other stuff, like, you know, I want to control a tape drive, so I might have to use a special tool to do that. There are some other things that kind of have a few exceptions there. One of those on recent systems, so on your desktops, is the UDEV. UDEV, which basically handles detecting devices on your machine. You know, I plugged in a USB stick into my laptop, okay? So the kernel detected a new USB device. The job of UDEV was to go and figure out what modules needed to get loaded. OK, USB storage, put that in, send my notification further up into my desktop environment, have the little window pop up containing the contents of my USB stick. But there are some applications, some utilities that kind of sit here a little bit outside. All right. Don't worry, it's fine. Okay. So examples of these things, applications include the GNOME desktop and everything that goes alongside it. They make use of the C library. And the library functions that they call are usually wrappers. So I'll give you an example in a minute of a very simple library function that we can write just as an example to show you what I mean and how they abstract this interface between the user and the kernel. Okay? And again, as I said before, the interface has to remain stable. That is not true once we get inside the kernel itself. So when you start looking at extending the kernel in new and interesting ways, porting it to new devices, making arbitrary decisions there, seemingly arbitrary, that change how things work internally, that's allowed. As long as applications don't see that change, that's fine. We don't have a Linux driver model, okay? So when you have a Windows machine, you get a Windows driver, okay? And the reason that works is because there's a stable interface within their kernel itself. They enforce various APIs within their kernel. Okay, so if I have a driver that I'm given for a Windows machine, then I know internally there are various kind of guarantees with respect to how things work. That's not true in Linux, and the reason it's not true is because we want people to have creative freedom to change anything, anytime. We're trying to encourage people to open source their drivers, to put them up into the Linux kernel. If you extend the kernel, add a new feature, the whole system is geared towards encouraging you to push that back up, upstream as we term the phrase is used, to try to get this back into the official Linux kernel so that you don't have to worry about any of these things. Okay. So this is a little demo. Don't worry too much about it. But basically I've got a little bit of code here, and I'm using this little macro defined in one of my header files. There's a syscall macro I can use to... Sorry, do you have a question?
Yeah, why are you using Linux/unistandard.h, not unistandard.h and user include?
Yeah, this is because this was tested on a PowerPC box. I had some weird. Yeah, this is all right. Ignore that. Okay, pretend that's not there. But essentially, I'm calling a macro here. Okay, and I'm saying I want to define a new system call. So in this case, I would like to be able to find out what my current user ID is. Okay, return that information to me. So I can use this macro that's provided in my system C library header files to define a new system call. Okay. Now I'm not going to go through this too much. You can take the slides afterwards. They're on the website. You can go through this, and you can see that in our header file, there's a macro here. We can specify what the function we want to use is called, and it will go ahead and look up in the header file to find out, how it should call into the kernel to create this new system call. I don't want to kind of get into this too much because we haven't got time to really dwell on it. But if you go through my example code later on, it's on the website, you can see how you can build up a new system call. Let's not worry too much about the internals. Let's just worry about the fact that once we've added a new system call to our system, when we call this program, we can ask the kernel something. So we can say, tell me what my user ID is. Okay? And it will return that information. So having defined it, okay, I can now call getUserID. And what will happen here is my C library knows how to ask the kernel to perform this function. It will ask the kernel, okay, what's my current user ID? The exact way it does that is kind of not important, but the result comes back. Okay. All right, so what we can do, the important thing I'm trying to show here is that we can trace the execution of this utility that we just wrote. We can see when we call this utility, we can trace every single call we make into the kernel to perform whatever the function we want the kernel to perform on our behalf is going to be. When we ask it to return the current user ID, it shows up in the listening here. So you use the strace command, and you can see every single thing your application is asking the kernel to do on your behalf. That's what strace does. Okay? So it's on your system. Play around with it. It's one of the standard debugging tools that you have. You've all seen GDB, or you've probably all heard of GDB. If you've done any C development, you've got tools like strace sitting there you can use to figure out, okay, what was my application doing? What was it trying to get the system to do for us? So that's the whole point of the last couple of slides. As I said, if you really want to go into the example, it's on the website. You can download it. Knock yourselves out. Okay. So, this is the next bit I want to just address here again is on this slide here we talk about these system utilities. I just want to quickly touch on this. Again, this is a very kind of quick overview of the system. I know I'm rushing through this, but I want to get on to the more sort of sexy, interesting stuff. So what the system tools and utilities do, well, the kernel provides some functions that we can use for which there's no kind of standard way of using that functionality. We have to have a special interface, a special mechanism. For example, the new event stuff in kernel 2.6. I plug in my device, I get notifications propagating up into my user space programs telling me something's happening. We need ways to handle this kind of thing. We have these things called ioctls. Again, another sort of special case type of function I can use to communicate with my kernel. It's completely out of band. It's nothing to do with sort of standard programming practice. And there are many other tools and utilities on your system that are using these kind of special case interfaces. So these things sitting over here. Okay. We're not worrying about that today. I'm just mentioning it. We're worrying about this, and then we're worrying about what's happening inside the kernel here. So, okay. Here's the example I gave just now of something a little bit different to do with utilities that get called, inserting a USB stick. But again, I don't want to dwell on that too much. I want to get on to the kind of internals. So, all right. Let's look at the kernel itself. That's more interesting than looking at the system as a whole. That's what we're here for today. Okay, so what's the history of Linux? Well, I think we all know that Linux is, dates back to 1991. We've probably seen Linus's original posting when he announces he's working on this small operating system. Won't be big and interesting like Unix, or however he said it. The point I want to make is that, okay, so that was an Intel 386 machine in 1991, but it wasn't too long after that people started using Linux on lots of different kinds of machines that, Linus had never envisaged that it would be used on these. So the Motorola 68000 was an early adopter. We had Spark. TiVo's interesting, the PVR company, yeah?
The Alpha.
Alpha, yeah, it's not an exhaustive list, but the Alpha was an early one as well, absolutely. And again, I should have probably, considering I'm in Boston, I probably should have put Alpha on that list.
Yeah, because we actually demoed Linux on the Alpha in what, 94 or 93?
Something like that, yeah. Again, I should have put it on it anyway. But so the reason I wanted to mention TiVo there is because everyone's heard of TiVo, right? Whether you know of Linux or not, everybody's heard of TiVo. Everyone in the US and pretty much everywhere else as well. But the TiVo was very interesting because in 1998, when they started working on this, they decided to use Linux. They decided that, You know, Linux was not really geared up for what they wanted to do with it, but we don't care. We're gonna make it do what we want. We're gonna adapt it. We're gonna make it work on our devices. So if you look through the Linux source code, you'll see the name TiVo mentioned a lot of times, especially in the PowerPC part of the Linux kernel, which is what their system's based on. I said mobile phones there. Sorry, these slides are based on a talk I gave in London. Of course, I mean cell phone in the US, but a large number of cell phones now are also running Linux. Okay, I don't have any with me today, but somebody probably has one somewhere. Okay. We now support 20 different architectures. I'll go into what an architecture is. I'll explain these terms a bit later on, if you don't know what they mean. And it's relatively easy to add more. Now, new architectures don't come out very often. You know, we've heard of Intel 386, the IA32, which is the technical term for it. We've heard of Motorola, we've heard of Spark, we've heard these different terms. We don't tend to get new architectures very often, but you can add more if you want. Also, early on in Linux development, we added kernel module support. So, pretty early on, it becomes possible to extend the kernel after it's running. So you want to add support for a new device, new hardware. Okay, you can do that, and even after your system is booted. Now, today, if you're using Solaris or a proprietary Unix system, you know, that's not big news to you. You can do it there as well. But when this started happening in Linux, you know, there weren't too many other Unix systems or Unix-like systems out there where true module support existed. We also have evolving documentation, new sites, and I'm going to give you some links at the end that point to some more resources. So, getting hold of the Linux kernel, well, I think everyone's heard of kernel.org. If you haven't, then that's the website. Sorry about the blue. That's OpenOffice, converting links to blue. But you can get hold of the source in two different ways. You can get hold of an archive that contains the latest Linux kernel sources from the website, or you can use one of the development tools that I'll go into in a moment for getting kind of the state of the art, tracking what's currently going on. If you just want to check out any Linux kernel, go to kernel.org, find the latest kernel. As of today, it's called 2618.2. Download the archive, unpack it, and that's what you'll see within it. Thousands of files, broadly under those directories there. Regular development is tracked using a tool called Git. Some people pronounce it JIT. And the point of Git is to allow distributed development. So we have developers here, we have developers in Europe, we have developers in Asia, people all over the place who all want to contribute, and that has to be done in a globally distributed fashion. So some of us know the history here. For those of us who don't, various tools have been used in the past, and roughly speaking, a year ago, the tool that was being used, the license changed, became non-free. It was not possible for the Linux development community to continue to use it in the way that it had been used. And Linus Torvalds, who's obviously famous for writing the operating system itself, decided to write a tool to track development, a source code management tool. And as we know, now, within 2 weeks, he had re-implemented all of the functionality that was necessary. So 2 weeks, he goes from having nothing. He says, okay, I'll be back in a week or two. And he comes back and says, hey, look at this. And of course, it does everything that they wanted, and he'd done the work of a company in 2 weeks. You know, that's the sort of thing that happens. If you follow the website, kernel.org/git, you can download this tool. You can use the command git pull on a daily basis to find out, you know, what's changed, pull down the latest changes to the kernel from the kernel.org website. Again, on the website there, it will tell you how to do this. Don't worry too much about writing this down. The slides are online anyway, so don't worry too much about that. The key point being, we use this tool to pull down sources on a daily basis, and we follow along what's going on using the Linux kernel mailing list. as a reference. And the kernel mailing list basically is kind of, well, it's where all the open discussion happens. You know, I'm not going to say private discussion doesn't happen between kernel developers. Of course it does, right? Because they want to debate issues and they do have private exchanges. But for the most part, the development of Linux is far more open than any other system. Okay, and a good way of tracking it, if you don't want to subscribe to the mailing list where you're going to have hundreds and hundreds of emails all the time, is to go to lkml.org, which is a third-party site that sort of nicely tracks all of the kernel threads, shows you what's most popular, shows you, who said the most interesting thing this week based on the number of people who've looked at the email thread and all that kind of thing. It's a very interesting resource. And later in the presentation, I'll show you some resources, including Linux Weekly News. Linux Weekly News is a great website to check out, lwn.net. And what they have there is a weekly email that goes out, kind of updating you with what's going on in the Linux kernel community this week, and also in other different communities too. But their coverage is far more comprehensive than, even if you sit there and read every email, even if you have that time to do that, somehow their coverage is even more comprehensive than that. They really, really do know what they're doing, and they really do have a lot of great people contributing to the stories that they put out. You can also use a tool called GitK, which is a graphical tool. Rather than kind of trying to go through all the textual output of the Git command itself, you can use GitK, you can visualize what changes happened to the kernel today. Okay, as you read through the documentation, it'll explain more, but I'll just point out a couple of things to you. The key one being that Linux kernel development does not happen in terms of changes to a file. Okay, we have this concept of a change set. So we don't change one file, we don't change one thing, we change a group of things. Okay, and that more accurately reflects actual software development. Okay, it's not John changed foo.c, it's John changed some stuff in order to fix bug number whatever, right? That's more along the lines of how people actually write software. So Linux kernel development happens in that way as well. Changes are tracked in terms of change sets. So we can trivially and easily say, okay, change set number, whatever, introduced a bug. Let's back it out, and it will pull out all the different changes that were made in that change set. So that's what you see when you go through the list here. You're seeing collections of changes to the kernel. And you'll get a nice log, ridiculously long. We're now at the point where, on a monthly basis, more changes happen to the kernel than, at some times in the past it has been in total size, right? So we're looking at like 10, 20, maybe 30 meg worth of changes to the kernel in a very short space of time, okay? Huge numbers of changes are happening all the time. New features get added, things get removed, okay? And pretty soon that the size of the changes does add up to quite ridiculous sizes, it really does. So you can check out this tool, it's pretty cool. It's probably already in your distribution, so you can just apt-get, yum-get, yum-install, sorry, or whatever your favorite tool or command is. Other source for the Linux kernel is your vendor that you got your Linux distribution from. So, you installed Fedora, okay, well it went, your Linux kernel source went in there, but different distributions have it in different places. The point being, your vendor has supplied a copy of the Linux kernel source along with the distribution. They've made changes to it. Okay, vendors make changes to the Linux kernel as part of the process of their development. What they do is they add fixes for known issues that specifically affect them and their customers. Okay, they add other features that are being currently worked on that are maybe not in the official Linux kernel yet, but will be soon. Maybe they'll put a cute penguin logo or change the penguin to a chameleon or whatever. I mean, all kinds of fixes get added. So it's not the same as the Linux kernel you could download from kernel.org, which means that it's not useful for porting the kernel to a new device. So if I want to make Linux work on something new and interesting, I actually want to go to kernel.org and download the source code from there. I do not want to use the Fedora kernel sources to build a kernel for this. Okay, that's not what it's been geared, designed for. Having said that, if you are doing development, you are working on Linux for interesting gadgets and devices, then some of the vendors in that space who will sell you embedded Linux products, they intend for you to take their kernel sources, their special modified version, and to use that instead of the kernel.org source. Sometimes they'll do this if they've added their own features, their own drivers, their own additional options that they want you to use. But generally, you want to use kernel.org as much as you can. Okay. So, I'm not going to go through all of this because it would take hours, but configuring the Linux kernel, after you've downloaded the kernel source, you want to use this command, menu config, make menu config, to configure up the kernel. You want to choose which options you want to build in, which kinds of disks you want to support, which kinds of USB devices you want to support, what kind of file system. You know, do you want to support your ext3 file system that's on your hard disk now? Do you want to support the Andrew file system because you've got a server, you know, a few thousand miles that way, and you'd really like to use its storage as well? You can configure different options. Most of the time, your vendor will have configured your system with pretty much everything built as a module. So anything that can be built in a modular way, that is to say it can be loaded later, it can be added to the system at a later time, they will have built it that way if possible. After you've configured it, you run make, and you wait a while. A lot less time these days. You know, I still remember the days when you were looking at 6, 7, 8 hour compile times. You know, now you've got to wait 20, 30 minutes maybe. You compile a lot of things in there. You go make a coffee, come back. Standard kind of thing. Okay. After you've built it, you can install the kernel. You need to install it, you need to make it available. You need to set it up so that when you start your system, it's going to be used. So the first thing you do is you install the modules that your kernel provides, anything that can be added to it later. They live in a standard location. So you want to install those using the make modules install command. You want to install the kernel itself according to whatever instructions your Linux vendor provides. Again, it does vary from one system to another. Broadly speaking, they live in /boot. And broadly speaking, there'll be some kind of command or utility that your distribution provides to wrap this all up for you. So you can, in the case of Red Hat, you can run new kernel package, and its job is to kind of handle a few of these things for you. So you will have to follow your distribution guide. The exact process will vary. Okay, so that's how you build a kernel. That's how you configure it. That's how you build it. That's how you can reboot your machine and fundamentally be at the same point you were at 10 minutes ago. So what was the point in building all that stuff? Why did we bother? I mean, you know, we're still at the same point we were at. Well, not really, because we're not going to be able to write any drivers for our system. We're not going to be able to extend our system unless we have built the kernel sources. So we've now done that. We're now at a point where if we want to write new drivers, new modules for our system, we can do that. We can take the source we just built, we can use that as a reference to build modules for it. So we can add new drivers, new kinds of hardware. If I get a new PCI card for a new sound device, something like that, I can build a driver for it. I can add a new file system. You know, if I want to use my Gmail account as a file system, someone has written a driver to do that. And there are different ways of doing that as well. You can use Fuse or you can use kernel modules, all kinds of different things. You can't change the core kernel. You can't change something that's fundamentally in the kernel through a driver or a module. So for example, if I wanted to change fundamentally how Linux views memory, at a very basic level, I can't do that in a module. That's not what it's designed to do. Modules are designed to take the interfaces and features that are already provided by my kernel and add one specific new thing, one new kind of device, one new kind of file system. They're not designed to go and change everything underneath it. So sometimes you have to modify the kernel itself. We'll talk about that in a minute. So here's a sample module. It's nothing too fancy. If you want to get more into modules, you're going to get a hold of one of the books and read it. It'll go through how to actually write modules for different kinds of device. But this module here simply prints hello world to the kernel ring buffer, the kernel log. You can go ahead and view the output by checking in your system logs. So you can compile up this function. When it's loaded, it's going to print the message hello world into our system logs. I'll show you how to get that out in a minute. The point is, here's an example. It's not too long. About a page and a half of text, including some documentation here, module author, description of what the module does, and the license, very important there. These are standard macros here that you always include that provide sort of information about the module. The license is important. If you don't provide a license, then when you load that module later, the system is going to think it's been tainted. It's going to think that you've added a module that's not GPL, that's potentially proprietary. That means that your system, your kernel itself, is no longer purely GPL. That's where these taint messages come from that you may have seen in your system logs before. So you need to have a license in there. Okay? I'll just kind of cover a couple of points in this. Yeah, Chris?
John, where's the hello world function being called from?
Sorry, yes. It's a very valid point, thank you. I need to remember to change my slide back again. Okay, so...
He exports the symbol.
Yeah, I export the symbol hello world, okay, but I don't actually call it. Chris is right. When you load this module, you get loaded module printed into your log, and you get unloaded module printed when you remove this module from the system. The actual call to hello world, I did actually take out. But if you put in a call here to hello world, then you could call it. The other point being, I have this macro call here, export symbol GPL. Thank you, Chip, for pointing that out as well. I'm exporting this symbol, so it means that I'm making that hello world function available to other modules in my system as well. If I want to build up a set of modules that use different functions from each other, then I have to say, I want to make this function available to other kernel modules. So I have to have a line like this, export symbol, in order to make that function available. So no, I don't call it here, but if I called it somewhere else, now when I go ahead and build up some other module, it can figure out, okay, I need to have this hello module loaded first in order to make that function available. Okay. Now, just let me cover a couple of other points here. So, if you ignore the left-hand side here of this example, and you just concentrate on the right-hand side, you'll see at the top we have the metadata about this module. Okay, we have defined entry points. We have a macro here called module init that says when this module is loaded, call that function. So whenever I do a mod probe or an ins mod and load this module on my system, it's going to call this function here, hello init, that's been specified. Whenever I remove the module, whatever's in here, module exit, is going to get called, and that's going to result in a call to hello exit, which will result in unloaded module being logged into the system log. It doesn't go to the screen. Where would we put it? We don't have like a kind of fundamental concept of a screen to which all kernel messages will always go, where the user's always going to see them. There might not be a screen on my machine. So they'll go to the console, but we won't get into that too much. They're not necessarily going to be visible by the user, sitting in front of a machine somewhere. They're going to go into a log. That's what printk does. Prints the message and puts it in a log, which we can then view. I'll show you how to do that. So first I'm going to take the source code I just wrote for the simple module. I'm going to build it. In order to build it, I need to have this kbuild file. I need to tell my Linux kernel build system how to build this module. Okay, so I put in a couple of entries in a file here. I say, okay, I'm going to add a new module. I'm going to call it hello module. And by the way, hello module requires hello to be built first. So simple make rules, okay, for those that have written make files before. And then when I make a call to the make command from within my existing kernel source, I can build this module for the kernel that I built before. So I write a simple file here, I call the make command, and at the end, out comes a module that's been built against my kernel. Again, you can download these slides. You know, there's no point kind of going through every single line. I'm trying to make the general point here. If you want to go through the example line by line, then please download the slides later. You know, go through them, and you know it'll make sense, I hope. If it doesn't, you can email me, and I'll try to explain it. Okay. You need to install that module. You need to make it available. Otherwise, your system's not going to know how to load it. I can sit there, I can type mod probe until I'm blue in the face, but you know, unless I've actually put that module somewhere, I'm not going to be able to use it. So I make a call to modules install. It puts that module into the lib modules location where all my standard system modules are located. Okay. Having done that, I can then use my mod probe command, mod probe hello, and I can check in my system logs. I can see it's reported that it loaded the module successfully. I can also remove the module, again using the mod probe command, and I can see in my logs the module has been removed.
There's turning the lights down just a little bit.
Okay.
I'm trying to.
Okay, so before I get on to the next section, are there any questions about, I know that was very quick, it's just I'm aware that we've only got a limited period of time to cover a lot of stuff here. Are there any questions about configuring a kernel and building up the example? No questions from those? Yes?
So you exported a symbol,
Yeah.
and I was wondering if I can still call that symbol when the module isn't loaded yet.
So yeah, when
yeah.
you so okay.
So would it mod probe for me if I call hello
Yeah,
world from
when you
another?
So when you've built the module using the make command there, you make this called a detmod. And detmod generates a bunch of files under lib modules. Not only are your kernel modules themselves located there, but also a file called modules.det. There's a PCI aliases file in there as well. So if you've ever wondered, how does your system, you know, when I plug in a new sound card, how does my system know that it's got to load that driver? I mean, it's not magic, right? What we can do is we can actually provide that kind of information through macros as well in our module. So that when we run this detmod command, and most distributions will either call detmod when they boot up, or they'll have some kind of process for automating rerunning detmod for you as well. But when this runs, I also produce other files that contain information about, here are the drivers that support this PCI device, or here's the driver that supports this other device. Here's the dependency information. So the dependency information is also generated at this time. If I have another driver I'm going to load, and it has a dependency on my driver, that's how it gets resolved. The other driver's been built, this command has been run, it's all worked out. Okay, if he tries to load that module later, I'm going to have to load this one first. Okay, so that's how, if we provide a new symbol, that's how, you know, if someone wants to come and use this, during the build process, it's going to work out, okay, there's an unresolved symbol, what do they need? They need hello world. Okay, what other module provides that symbol? Okay, there it is. I'll put that into the dependency tree, so when the other module gets loaded, this one gets pulled in automatically. That's how automatic module loading actually works. It's not magic. It just relies on non-circular dependencies. So for example, I can't have two modules mutually depending on each other in sort of complex circular fashions. That's not a good idea. That's not resolvable. I can't sort of load this module, oh, but it needs this, so I better load this first, but it needs, I can't do that. So I have to have kind of simple dependencies here. Okay? I don't want to get too kind of in depth here, because I can kind of go off on a tangent for hours, and then people are going to really hate me. So I'll avoid that. All right, but the point being here, if you go through the slides, I'll put them on the website. It's people.redhat.com/JCM. They're not live right now. I'll just change the file permissions later and they'll be there. But I'm one of these people that like to sort of make sure the slides are there, but not sort of have them available before the talk, because then the talk's still interesting and everyone hasn't already read my slides and knows what's going to be on slide number 23. Okay, so that's how to build a module and how to kind of figure out what it was doing. Right, let's talk more about the kernel architecture. That's fun. Okay, so how do I view the kernel? I view the kernel as a privileged software library. Okay, I like to use that concept. Not everyone agrees with it, but the idea that basically the kernel is not a magical program. Okay, the kernel is not something that runs on your machine all the time. People talk about it like it's this all-seeing thing that's constantly running and constantly doing stuff. That's not true. Okay, the kernel is more like a collection of functions that occasionally do things I want. Okay, and primarily those functions get executed for two reasons. Okay, for two different kinds of reasons. They can be asynchronously called or they can be synchronously called. Okay? By asynchronous, I mean things that happen all the time, no matter what else is running. So, on a standard Linux machine, 1,000 times a second, configurably, I have this timer that goes off. Okay, so 1,000 times a second, I get this timer that fires. The hardware at my machine interrupts whatever else is going on and says, tick. Okay, 1,000 times a second. Your machine's sitting there doing this. Tick, 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 tick. 1,000 times every second. Why does it do that? Well, it's convenient for us to schedule certain things to happen from time to time. And it turns out one of the easiest ways to implement that is to have everything be interrupted 1,000 times a second so that we can perform housekeeping functions we might need to do or a whole manner of other things. That's an example of an asynchronous event that just happens. We don't really have any control over it. Hard disk, events, a piece of data becomes available, a network packet comes in. These things kind of tend to happen, whether we do anything, whether we're running a particular program or not, we're still going to get these kinds of events coming in. Okay. We also have synchronous entry into our kernel, and that happens primarily through system calls and things that we ask the kernel to do on our behalf. So if I want to open a file, if I want to read some data, if I want to write some data, whatever I want to do, if I have to ask my kernel to do it for me, then that's a synchronous entry. So that's two fundamental ways we get in. The kernel's not sitting there kind of in its almighty, some kind of magical context, just sitting there saying, I'm running. It doesn't do that. It's not doing anything most of the time. Most of the time, your programs are running. That's what your machine is there to do. Every once in a while, a piece of code runs that's in the kernel, a privileged piece of code, to perform a specific task. That's what the kernel really is. Nothing more than that. It's not magical. It performs tasks on our behalf. It is privileged. That's the key point. So the kernel can do almost anything, right? Your program cannot. In order for us to maintain this kind of multi-processing concept, this notion that I can run a program here and Bob can run a program there, and they don't interfere with each other, and generally they can't kind of screw each other over, right? That's the whole point here. That's why we have this concept that your program cannot do everything within the machine. It has to ask the kernel to do some things on its behalf. Okay? So it maintains a fundamental software abstraction. It maintains this concept of a process, this concept of a running program. You start the program ls, you start the program bash, you type the command finger, you know, whatever it is that you want to run on your machine. When you run that, that's a program that's running. It's a process on your machine. If you run the top command, the ps command, any of these standard commands, you'll see a list of all the processes running on your machine. You know, on your desktop machine, you'll see, you know, a GNOME terminal process running. It's running your terminal session that you're currently sitting and typing commands into, unless you configured something else as your terminal, in which case you probably know what GNOME terminal is because you got rid of it, and in that case, your other alternative will be there instead. Okay, limits access to shared resources. The kind of old school example is, I want to print something. That guy wants to print something. We can't both print something at the same time. So, you know, we're aware that we have this concept of queuing up print tasks. Well, there are similar concepts at a much lower level for even more basic resources in our machine. Similar kind of mediated control, mediated access, where the kernel is able to decide who gets to access what and when. It's there to help us, not to hinder us, and the goal is for it to be as lightweight as possible. Okay, so the goal here is the kernel's not kind of needlessly doing lots of other stuff. It's basically there to help us to do what we want it to do. That's why we bought the computer. We bought the computer so that we could run our Apache web server. We did not buy the computer probably just to sit there and run the kernel all the time. There's some people who enjoy that, but that's probably not what it was bought to do. So here's another scary diagram. You see, I need to find a better way of doing diagrams. I do these in dia. I export them as transparent PNG files, and you import them into OpenOffice, and it doesn't care if it's transparent. It'll still put a nice white, horrible background there. And I need to find a way to fix that. But this scary diagram shows two processes running on my machine. Okay, so let's say this here is an ls command. Okay, this here is also an ls command. Two different users running the ls command on my machine at the same time. Okay, so what happens? Okay, I got two different programs, the same program, but two different people are running this program. So they're running the same code. Okay, they're both running the ls command. Okay, so our system is not going to load two copies of the ls program itself. It's going to load one copy of the ls program into memory, and it's going to share that between the two people that are using it at the same time. Okay, they're both running the same code. They're both physically running the same code that's in memory, stored once in memory. Okay, and they're getting different results. Why are they getting different results? Because of one of the fundamental things that Linux is doing is managing resources. Okay, the kernel is setting things up so that both these guys can run the same program at the same time, the same code, different data. Okay, and it's maintaining this independence between the two. It's not allowing them to corrupt each other's data. If one of these programs attempts to change some of the data, so my ls command, has some data structures within it. The compiled ls command has some internal data structures that are used while it's running. They get changed. One of these programs tries to change one of those data structures. The kernel is sitting there, and it's automatically keeping, effectively, just the changes my program is making. So it's maintaining all this fancy kind of abstraction, this fancy separation between processes. That's what my kernel's job is to do. Its job is to run processes and to handle resources that those processes require. Okay. So, different kinds of ways we end up in the kernel. Interrupts are one. So I already mentioned the timer interrupt. If you go through the source code on your machine, you can figure out, the different ways in which interrupts can come into your machine. Timer being an obvious one. Here's an example of some of the code for PowerPC machines that covers the timer. Okay, synchronous kernel entry. We already mentioned system calls. What else can happen? Various program exceptions could occur. I could try to access some memory that was plainly not my memory. My program's going to segfault, it's going to crash. The kernel's going to have to handle that while the program's running. It's going to have to handle accesses to data in memory. It's going to have to handle, okay, my program just tried to put something onto its stack, but that actually means that its stack is now bigger than the stack I had allocated for it. Okay, so it's going to go ahead and allocate it some more memory. And all these things are happening for us behind the scenes. If you want to look at more within the kernel sources, this is the kind of layout here. What I'm going to concentrate on for the rest of this presentation is the Arch directory and the kernel directory, which is what we're sort of interested in when we're porting Linux to new machines. But some other key directories to look at. We've got documentation. We try to keep an updated set of documentation, documenting changes we make to our kernel. Drivers here contains the drivers that we use in our machine. And a very important file here, reporting bugs. Okay, that is a great file. It tells you how to report a bug when something goes wrong. If you don't know how to fix something, it tells you how to find someone who does. Okay. So then coming on to the main topic, the main sort of reason we're here, kernel portability. Okay, so I had to go through that kind of crash course in kernel building and modules just to make sure we all have some basic notion of these things. But what I really want to talk about is how the kernel is portable from one device to the next. And I'll just stop for a second here and tell you a story. I like stories. This one's about a company I used to work at. As I said, we used to make giant magnets. More specifically, what we used to do was to make imaging systems for MRI, you know, and for measuring samples, for doing all this sort of, not just hospital kind of MRI machines where you can view someone's head, but machines where you can view the inside of a watermelon. Okay, here's another one for you. Did you know that the Japanese love to use MRI machines to look at the inside of watermelons to determine if they're ripe? And if no, it's true. And actually,
dedication.
And actually, you can charge $400 for a watermelon you've put into your custom-designed, custom-built MRI machine that can 100% tell you, yes, looking at the graph here, we can clearly see that yes, the water distribution's about right. It's got the right density and consistency, and it's probably right. Okay, $400 a melon if you can accurately determine.
I'd rather buy 200 watermelons and hope one of them is.
But you see, they don't want to do that. They want the guarantee that when I buy that, it's going to be 100% perfect.
For a gourmet high-end restaurant?
This is, I never really spoke to the customer. I'm assuming this is sort of restaurants, I hope. I'm hoping it's restaurants. If it's supermarkets, I'm worried, but I'm hoping it's restaurants.
For my cat.
But the point being that this is a machine that, you know, we've all heard of an MRI machine, we've all heard of going to hospital and having an MRI scan, all this kind of thing. So I looked at this company, we wanted to do something different. We wanted to test out Linux in a new and interesting way. And previously we'd been using DOS and other older operating systems. You know, Windows did factor in there, but not so much. Windows isn't really geared up for having demanding tasks where we, you know, have deadlines, we want things to happen when we say. Windows likes to take its time and think about doing it, and it might get back to us next Tuesday. So we decided to use Linux, and it was a fascinating learning experience because essentially, you know, this is not the board we used, but for sort of dramatic effect, I'll hold this up. And you know, we took a board like this. We designed the hardware for it. We figured out, okay, what are we going to want? We're going to want to have The processor sounds good. That sounds good. We want the machine to be able to do something. That's great. We want to have some memory. We want to have some flashing lights, because people like those. We want to have some high-speed data interconnect, so we can talk to our magnet and control its temperature. We want to be able to do all kinds of control in real time. So we would define all these different pieces of hardware that our machine would need. And then we figured out a way of getting Linux to drive all that stuff. Okay? So what I'm trying to say is there's nothing quite like having a real project to learn this stuff. You know, we started out really not knowing a lot about porting the kernel from one machine to another. I dabbled a little, but never actually had the job of porting the kernel to new devices. And we learned through trial and error. You know, I'm going to go through the material here, but essentially what I'm going to try to tell you is the best way to figure this stuff out, honestly, is to just go and do it. Yes, Chip?
What kind of suit do you do?
Oh, it was a, yeah, actually that's an interesting story as well. It was actually an FPGA, which some people have heard of and some people haven't. It was a field programmable gate array. It was a processor that didn't exist until you turned the machine on and you told the logic gates how to arrange themselves. Okay? People like to use FPGAs to build custom logic. For devices where it's not worth paying millions and millions and millions of dollars to have a custom piece of silicon made. I want to just be able to define my logic and use it whenever I please. You can get these devices that do that. I want to design my own CPU. Okay, fine, I can do that. It's not going to be as powerful as my Intel desktop computer. It hasn't got real silicon powering that CPU. Well, there's silicon in there, but in itself it's not a hard silicon product. It's configurable. I'd really like to be able to show that to you. And again, if we do a second session, I do actually have a couple of FPGA boards where we can kind of define our own computer and then build it in front of us and kind of port the kernel to it. And it's all very interesting because it's not even necessarily real hardware. It's a piece of logic. I'm telling it what to be when I turn it on. But this was a PowerPC type device. Okay, this was a PowerPC, so fundamentally not too dissimilar from my laptop, which is also a PowerPC. This is a PowerPC. So, you know, that's a PowerPC 405. That's a Freescale Motorola 7457. You know, who cares about the number? The point is, that's a PowerPC, that's a PowerPC. These are all machines that are related but not the same. As part of the next section here, I'm going to explain to you what I mean by, you know, the difference between one PowerPC and the next. What the hell does he mean? Well, I'll explain it to you. So let me get on to that. I can show you some of these cool gadgets I've got. So what is portability? What does it mean to have a portable system? Okay, so broadly speaking, it means writing software that can be more easily adapted from one machine to another than rewriting the whole thing from scratch. Okay? So, you know, Windows might be portable to this device in the sense that I could perhaps get Windows running on this device faster than I could rewrite the whole of Windows from scratch. But we might not necessarily call that portable. It meets that definition. We want to constrain this a little bit. I think we want to add in a reasonable amount of time to the end of this definition. So, in terms of Linux, I want to have it be the case that a new device comes out, I want to put Linux onto it, and I really want to be able to do that in a matter of weeks, not months or years. I want to be able to sit down and spend 2 or 3 weeks worth of weekends and get the system to a point where it can do something. It may not implement all the features and functionality that I want, but you know, I can boot it and I can say hello world and do some very basic stuff with it. We want that to be reasonably achievable in weeks, not months or years. Okay, so that's portability. Linux has no HAL, it has no hardware abstraction layer like some other operating systems do. So if you take Sun Solaris, okay, they have depending on the system, they call it ham, hat, how. There are different three-letter acronyms that mean the same thing. And these all mean that I have my core hardware, and I have this kind of HAL layer. I write some code in here, and then my standard system runs on top of it. I don't have to change the main part of the system. I just change a little piece here in my HAL, and magically the new device works. So the HAL's job is to kind of take everything I might want to do and wrap it up in some other function so I could replace that later. Yes, it makes the system very portable. It means that if I have VxWorks, if I have one of these proprietary operating systems that's designed for these kinds of gadgets, yes, it's very quick and very easy to adapt it. It's not very flexible either. So it hinders, if you had a HAL in Linux, it would hinder the ability for you to modify Linux as a whole. You'd have to maintain all these compatibility layers. You'd have to say, okay, so we're a big Redmond company, let's say, and we're going to have this hardware abstraction in place. We're going to have it be the case that you can write a driver now and it's going to work in a few years' time. Oh, but we want to replace that layer with a new one because it's more interesting. So what we'll do is we'll maintain that one, and we'll write a new one, and then in 2 years' time, we'll have another one, and we'll have 3. Every time we make a change, we're going to have to change 3 different places and make the change we actually wanted to make. Now, Linux doesn't really like that. The Linux community doesn't like that idea. It really likes the idea of making changes and not having to care. So that's why there isn't a HAL in Linux. There's no Linux driver model either. Yeah.
Not having driver model or HAL is nice for, as you said, the ability to modify things.
Yeah.
But then it also brings the problem of drivers breaking
Yeah.
between kernel versions.
Hence the reason that and also the reason why I cannot use this video out feature on my machine without using a proprietary driver. I don't want to get too much into the proprietary driver thing. I will say that part of my day job is very heavily involved in drivers and worrying about sort of compatibility between one kernel and the next. It's not entirely true that, this statement's not entirely true. So if you go out there and you take an enterprise Linux distribution, I don't just mean Red Hat, take SUSE, take the different enterprise Linux products that are out there, okay? A lot of those guys try to maintain binary compatibility from one release to the next. So you buy product version 3, okay, and forevermore, product version 3 is going to be set up so that you can take a driver and install it and it will work, okay? That doesn't mean that there's a stable HAL there. It means that the company is trying really hard not to make changes that are going to break compatibility with drivers for that specific release, okay?
What I wanted to ask you relating to that was, in some summary of the kernel mailing list, probably the one on Linux magazine,
Yep.
one of the past months, there was this note that one of the committers was sort of working towards
Oh, it's stable.
not quite having a stable driver model, but sort of a surrogate.
What you probably mean is Thomas Gleixner's work on user mode drivers.
I'm not sure.
Okay, I mean, I won't go off too much on a tangent, but there are some guys working on user mode drivers. These are frameworks that enable us to write a driver and have it be like a regular program.
Mm-hmm.
So we already have this for USB devices. We have libUSB there, so we can write essentially a driver as a program that runs and drives a USB device. Yeah, Chip.
It's a step towards a microkernel.
Right. It's a step towards a microkernel. It's a step towards, you know, macOS or Linux or something like that. It's not quite that far along, but yeah, it's a step towards saying, okay, well, if we're going to have binary drivers and closed drivers and all these things, we don't like them, but if we're going to have them, let's not have them in the kernel. Let's have them be, that's his motivation. He works in the embedded space. His motivation is to say, we know these guys like to have their binary drivers, their closed source drivers. We don't like that, but if they're regular programs, that's allowed. It's always been allowed to have a closed program. So if we can make it somehow so they can do that
And he has to create an API to be able to do that.
Yeah, I'm not endorsing that from the point of view that I think it's really cool technology. I think that as a concept, it makes it harder for you to use devices in a free way. So maybe we don't want to endorse that. Yeah.
Not to drive you farther off the topic.
That's okay.
But I was thinking about the security implications, but if you're doing drivers in user mode, then that means that whatever protections, whether it's whatever you've done to harden the kernel is actually strengthened, because you're not, with HD more launching this month of kernel bugs and so forth, and just hammering driver vulnerabilities. That would actually be a security plus if you're running it in user space, right? Am I missing something?
Well,
I realize that the portability, and when you get into user mode, you're restricting some things. From a security point of view, that would actually be an advantage, wouldn't it?
yes and no. I mean, I think we'll have to take that discussion into the part, because there are some real issues with.
I know there's a security alert this morning about something to do with the Broadcom.
Yeah, because
the Windows. That actually came out a couple of days ago. It's kind of been floating around for a while, but yeah, it's a closed driver. It exists for Windows, and there's a known flaw in it.
The alert said that Linux is vulnerable too. It's running an NDS.
Yeah, if you use NDIS wrapper, again, NDIS wrapper basically lets you take a Windows driver and load it into your Linux kernel. Right. You can't use NDIS wrapper on some kernels. It relies on certain kernel configuration options. It relies on 8K stacks, for example, right? It relies on having a larger stack within my kernel, so I can actually call into these functions and not run out of memory to call some of these wireless functions. So some distributions just don't support NDIS wrapper, and you can add it on. Some distributions don't support it, and you can add it. And some now ship NDIS wrapper as part of the distribution itself. So, next slide. Architecture ports, let's get down to it. What's an architecture? Well, an architecture is a fundamental type of new hardware. So, an architecture would be the x86, the IA32 original Intel x86 platform. Not x86 64, not IA64, but the Intel x86. That's the type of architecture. The IA64, the Power PC, the Spark, the Alpha. These are fundamental types of machine architecture, types of processor device. You get families within that. You get families of PowerPC, you get different models of Intel CPU, but they're fundamentally of a unique type. Okay? What does it mean to have an architecture? It means you've defined the language, you've defined what kinds of basic operations this processor performs, specifically, what numbers those are. So when I compile my program and it's converted into binary code, is that binary code going to be interpreted, going to be correctly executed by a specific CPU? Well, I compile it against a specific family of CPUs. So if I build my code for an x86 processor and I'm running it on an x86 processor, that's great. If I'm running it on an alpha processor, it's probably not going to do anything at all, but if it does, it's certainly not going to be what I'd intended it to do. Okay? So typically what happens is a hardware vendor decides, okay, we're going to create a new type of architecture, and they go ahead and do that. They've got a huge amount of invested interest there in getting adaptation. Okay, they would really like everyone to use that because they just spent a lot of money on R&D developing it. I mean, there's no point developing it if no one's going to use it. Some of us enjoy that, but generally, people want to make money out of things that they have developed. So there's a huge amount of interest here from the vendor themselves, the Intel, Motorola, IBM, in getting support for their new kinds of architecture. You need a lot of funky hardware at this point. You need to have really expensive pieces of hardware with experimental chips on. You need to have all kinds of hardware debuggers, little boxes I can plug into my chip, and I can stop the chip and figure out, okay, what was the next instruction that was going to run. So in the same way you debug your regular program, you can debug the actual instruction by instruction execution of your operating system on your processor. Okay, so that's the kind of tools that they have to have in order to get Linux or any other operating system to work on a completely new kind of architecture. And you need to port the different tools that you're going to use as well. So, you know, it's all very well trying to get your kernel to run, but if your C compiler can't actually compile code for that processor, then you've got to get that to work first. So in reality, you've got to get a lot of things done before you can even get Linux up and running on a new kind of chip. Fortunately, that doesn't happen very often. As I said at the beginning, there are already 20 architectures supported by Linux, and that's after 17 years, 16 years, you know, whatever, a long time in the development of Linux for us to get to the point where we have 20 architectures supported. Yeah?
You said that the Intel A32 includes not just the 86, but the AMD 8664 and the variant.
No, I didn't say that. I said...
You said not?
No, yeah.
Okay.
Yeah.
You didn't mean to include them?
No.
I was wondering, okay.
Sorry, yeah, when I say...
Power and PowerPC are the same instruction set architecture, essentially. They're two families within one ISA, so I'm wondering why are they separate?
Why am I separating them? Okay, so a bit of history. See, I knew you were going to ask that somehow. Here is the original PowerPC architecture manual. You can't buy these anymore. This took me 2 years to get hold of because I really like reading IBM documentation. And what actually happened with the PowerPC was that they needed to come up with something, they being the AIM Alliance, Apple, IBM, Motorola. They needed to work on something. IBM already had the power, so they got the power. Let's do something with it. Let's make a new kind of chip. Let's make it cheaper. Let's make something that's easier to mass produce for consumer use. That's maybe not as powerful as the big mighty power processor. So they reduced it and they called it the PowerPC. There's compatibility there. Some of the early chips, the 601 especially, was actually a modified power. Okay, but strictly speaking, they are two separate ISA, two separate instruction set architectures. Okay, you've got power and you've got PowerPC. There's a what's the term I'm thinking of? An intersection of the two. So they have a kind of common subset, if you like, of instructions that are shared between them both. But that's not, yeah.
Hey, I was just going to say, in one consulting job that I had to port an application from a very old version of AIX to a slightly less old version of AIX. And if you ever have to do that, you'll find out why Power and PowerPC are listed differently. Just the compiler options, to figure out the right compiler options to go from one to the other was a horror show.
Fundamentally, you could write a simple piece of assembly code that would work on some Power and PowerPC machines. But I do list them separately because they both extend the core ISA in different ways. They have their own instruction sets. But you're right in saying they share a common history, common ancestry. And the history of PowerPC is especially interesting if you're into that kind of thing. Again, there's a great book here and there's some great resources online that go into that in more detail.
So you're going to call the various flavors of 86 other architectures as well then?
In that sense, I'm going to call, well, I'm going to say the x86-64, I'm going to say that's a different architecture because we've made a lot of modifications there, you know, so we can have code that runs on that and does not run on a regular kind of x86 processor. Yeah, there's again, I'm not an x86 person generally. I try to avoid it. And the exact way that's handled in Linux has kind of always been a special case because that's where it originally came from. So a lot of the more recent ports have been much cleaner, much more separated. We are at the point where, so the PPC-64 and PPC-32, PowerPC, regular PowerPC and the higher end PowerPC-64, essentially one set of code was copied, renamed, and a few changes were made. That might not be the best way of doing it because there are a lot of things that they could share and don't. They just have straight copies of the same file.
Which is... they share.
they shared bugs originally, and now they diverge in their sharing of bugs. Some new bugs come up here, and some new bugs come up there. So yeah, there are ways to do this and ways not to do this as well. And I guess by spending way too much time going through the architecture code in the kernel, like I've done, you can discover these little amusing anecdotes. So anyway, the point being, it's very difficult to get Linux working on a new architecture. It's not something we do every day. They don't tend to come out every day. And when they do, a lot of work is involved. Okay, so architectural differences. Let's just give some examples of architectural differences. How do we define memory in our machine? Since I used memory examples earlier, I'm going to use another one. How do we define virtual memory? So we all know that, or most of us, I guess, in this room know that on Linux machines and Unix machines, and in fact Windows machines, and pretty much every other regular kind of computing device these days, memory in the machine is abstracted. We have this concept of virtual memory. We can use disk space to augment our memory and give us effectively more memory than we have in our machine otherwise. We have this concept of virtual memory. And that relies on various support from the hardware in our machine. It doesn't just magically happen. Okay, there has to be a way for the machine to execute instructions and to know, okay, I'm going to go ahead and access some data in a memory address, except that's not really where it is. It's really somewhere else, but I need to figure out where to go from the virtual memory to the physical memory address of that piece of data. So how that's implemented varies from one type of architecture to the next. Why does it differ? Because it does. Which way's up? Well, we heard we've probably heard the Indian story. For those that haven't, the story Gulliver's Travels, where you have the Indian people who constantly debate about which way up an egg should be when you are eating it. The name Indian was taken from that context and used to describe machines where they order numbers in memory differently, again, for seemingly arbitrary reasons. But people get very attached to the way their machine does things. Intel machines, little endian, people get very attached to Intel's way of doing things. IBM machines tend to be big endian. PowerPC can be both, depending on a configuration option in the processor when I turn it on. It's all very exciting. People get very worked up about it. So there are differences because there always are differences between two different architectures. How does Linux implement virtual memory? Well, Linux has its own implementation, fundamentally very similar to that that's used in the Intel architectures themselves, because that's where it came from. That's where Linux was first running, so that's where the implementation has come from. What it does mean is that if you're on an Intel machine, if you're on a regular x86 computer and you are using virtual memory, it's a lot easier for implementation within the kernel to function. If you're on a more interesting, huge IBM power server, then a lot more kind of hoop jumping has to happen within the kernel in order to in order to adapt how Linux does things for how the hardware does things. But the fundamental point here is there are differences between one architecture and the next. If you like diagrams, here's another one. So again, if I just take the notion that in my machine I have virtual memory, I have this concept of being able to have programs see memory however I like, the reality can be completely different. So here's my program, nice ordered memory. I can use memory address 1 followed by memory address 2 and so on. It looks all nice and ordered. In reality, it's all over the place physically in my machine. Some of it's not even there. This one of these pages here, one of these pieces of memory in my program may not actually physically be loaded right now. And when I try to use it, I'm going to get a fault, a page fault. My machine's going to have to go, my kernel's going to have to go and say, okay, this data's not there right now. It must be on disk. Pull it in, swap it in. Let's pull that data in again. Okay, so we've got all this kind of stuff going on. kernel has to worry about that. Implementation, again, varies. Intel do things one way. They have a concept of this tree hierarchy here, where I have an address in my program, a piece of data. I want to go and access that memory address. And when I try to access it, my processor knows, okay, I'm going to take my processor register, find out where my table describing memory is, find out where this memory address physically is really located by following through a bunch of tables. Or I might have something completely different. Might have a PowerPC 405, like this one, where memory is, there is no hardware support for virtual memory, where what happens is, every time I try to access a piece of data, processor says, what do you want me to do? And the kernel says, oh, okay, I'll work it out for you, and I'll tell you where that really is located. So sometimes it can even all happen in software. The point being, wildly different implementations to support something that we all take for granted. We all take for granted the concept that I run my program, it accesses data, okay? It's all just data, it's just ones and zeros. I don't really care how that happens. Architecturally, it might be very different from one type of machine to the next. It's just a concept. Everyone does it differently. Some people use giant tables. Some people do all kinds of weird things. It's just a concept. The kernel's job is to take this and wrap it up and abstract it and make it nice and the same for everyone. But it's an architectural difference. I have these differences between different kinds of processor. There's nothing I can do about it. Okay. So we can accept that for a second. What else do we need to worry about? Well, if I'm working at the kind of basic level of different architectures, I need tools that are able to build for a specific architecture. I need to be able to compile code for my particular Intel family of processor. I need to be able to compile code for my PowerPC, for my ARM, for my Blackfin 537, I think that one is. You know, whatever my different kinds of processor family are, I need to have tools that can compile code for it. I need to have a very, very complex kernel build system. If you go through the Linux kernel build system, it will scare you because it's very complicated, okay? They do a lot of hackery. They use these tools in very interesting ways. They weren't really designed to be used in when they build up the kernel. Partly because you know, you don't just compile the kernel. It's not just a regular C program. I have to compile the kernel, and I have to instruct my tools to physically place pieces of code in specific memory locations. So when they load onto my computer, they're going to be at physical memory locations that are mandated by my hardware vendor. Okay, my hardware vendor tells me if I want to write code for a PowerPC, if I want to write a kernel for a PowerPC processor, I have to arrange it so that some core pieces of code that it expects to find are at specific addresses in memory. Okay? Not like building a regular program. I have to use special tools. I have to use special linker scripts that tell the GNU linker, okay, this is how you're going to put it together. Try running a tool called, just one second, I'll come to the question. Try running a tool called object dump, obj dump, on your Linux kernel. Okay, and what you'll find, you want to run it on the VM Linux file, which is produced in the top level of your Linux kernel sources when you've built the kernel. It's a huge file. The object dump is even larger, and it will show you what the compiled code looks like. The point being that it's all neatly arranged with certain addresses being well known. For example, you see the top one there, C followed by zeros, 12 gig. That is the standard address at which my kernel starts. I just happen to know that. That's one of the standard things. So you can go through, you can look at these tools, and you can see how the different parts of the code have been laid out in the binary itself, following conventions. You had a question?
Yes, what do you mean by the third bullet there?
Check out dummy build. Yeah, explaining that quickly is difficult. That's the thing. If you go through the if you go through the kernel build and you look for there's a dummy stage during the build. Okay, there's a stage when the kernel's being built at which it effectively builds a program called dummy, and it does that in order to abuse the intended purpose of one of the tools to achieve something completely different. It wants to put all these different pieces of the kernel together. There's no standard way to do that, but there is a different tool that can roughly do what they want, so they call it in an unusual way, and they result in, the point is it's a hack. There's lots of hacks in there being used to put my kernel together for my machine. I want to finish at 9, so I'm trying to move along. Okay, so machine-defined hardware entry, yeah, okay, so I'm going to get hold of this chip from IBM. It's a PowerPC processor made by IBM, and they're going to give me a data sheet. It's a huge piece. It's not a, data sheets are not single pieces of paper. Data sheets are 1,000 pieces of paper, roughly described as a sheet. If you're some kind of giant, I guess it might be. But the data sheet will say, okay, in order to build a kernel for this kind of chip, you have to do these things. Okay, so I have machine-defined hardware entry. There's a machine-defined way in which my machine starts. There's a defined way in which my Linux kernel must be put together in order for it to work on that machine. There are machine-defined interrupts. There's concept of a timer, something that's running 1,000 times a second, telling me, tick, 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 tick. That's done differently on different kinds of machine. I need to support that. I need to support virtual memory. I need to do a lot of things. And ultimately, once I've done all that stuff, I want to end up at a function in my kernel where it starts doing useful stuff. So there's a function called start kernel. That's really where the first bit of C code comes into things. So up until that point, we're in the guts of the machine. We might be doing a little bit of C programming, probably a lot of assembler, lots of scary stuff. We end up running some C code that starts off the first process in my machine, starts managing memory, starts detecting devices, starts making those devices available, gets my file system working, those kinds of things. But we really have a lot of stuff to do before we can even start the machine, really doing anything useful. So, luckily, we don't have to worry about that very often. We don't port the kernel from one architecture to another very often. There's a lot of things that have to change. We don't want to have to worry about that. What we do worry about is platform porting. So what's a platform? Well, broadly speaking, this is a PowerPC platform, and so is this one. Okay? This is a PowerPC platform, and so is this one. Okay? And there are several other PowerPC platforms sitting on those desks up there. Some of them might be Intel now, who knows? But these are all PowerPC machines, but they're not the same. They're not the same model. They're different arrangements of the components within the machine, but they are fundamentally PowerPC machines. So they share that. They share that in common. They're based on a standard architecture. They're based on one of the 20 that we know of, that Linux already knows about. But they arrange things differently. They have different network adapters. They have different sound cards. They have different arrangements of the same components within the machine. What the hell's he on about? I mean, this doesn't make any sense. Well, let me try to make this make a bit more sense. TiVo runs on a PowerPC platform. Okay? PowerBooks run on a PowerPC platform. Okay? Industrial Linux is running on a PowerPC. GameCube Linux runs on a PowerPC. These are different platforms based on standard architectures. You know, I'm kind of glossing over the fact that there are sort of sub-architectures here, but I'm not really going to worry about that. Fundamentally, we have different kinds of platform built on these standard architectures here. We take ARM as another example. There's a PDA going around I gave out at the beginning. It's a Nokia 770. It's based on an ARM processor. Okay. This iPod that happens to run iPod Linux, it also has an ARM processor inside it. In fact, it has two. You know, Apple didn't want to kind of scrimp on processors, so they put two ARMs in here. There's a Broadcom ARM processor inside this machine. Okay, they're all ARMs, but there are different arrangements of the other parts of the machine. Okay. I'm not going to get too worried about the hardware differences because I think we would be here all night if I did that. But fundamentally, you know, we have the same machine, we have different configuration of the other components within it. So, that's all very well. Let's say we want to get the Linux kernel moved from a machine we already know about. Let's take the laptop as an example. Let's take this one. I want to take Linux and I want to get it up and running on different kinds of a different PowerPC platform that shares things in common with this one. Okay. So we select a hardware platform. We select the processor, the architecture requirements. We select the memory, the storage, the other components within our system. We acquire the necessary tools. If we're doing hardware engineering, we're putting this together. We might need to have hardware debuggers. We might need to have various electrical test equipment. We do all that stuff. And then we acquire the necessary software tools. Okay, so we need to get hold of some tools that we can use to build Linux for our new device. So you need to get a tool chain. A tool chain is a group of tools that you can use to do these things. That includes GCC, but not just GCC. It also includes the other tools you need in order to take an application and build it for a particular kind of computer. So you can grab one from your distribution if all you're doing is building another kind of PC-like system. But if you're doing something a bit more interesting, you might need to build or find one. The standard one we use in the embedded space is Dan Kegel's Cross tool. And Cross tool, you go to his website, you download Cross tool, you configure it, you say, I want a tool that can build a kernel to run on processor X, Y, or Z, and it will do that for you. And if you really want, you can pay a vendor to give you a flashy tool with lots of GUI gloss that looks really cool and costs a few $1,000 as well. It's the same thing, okay? So this is the same as this, but you're paying a lot more for this one. So, do this one if you want, but you can also do the other one, So, get a good book, okay? So you need to understand the Linux kernel. I didn't write any of those. I don't have any vested interest in any of those. I am working on this one, so don't ignore anything I say about the second one. But you want to get a book. You want to get Understanding the Linux Kernel. That's a great book. That's kind of here's 1,000 pages. It may not be 1,000, but here's I didn't even get it out. It's too big. It's in my bag somewhere. It's a huge book. It kind of takes the whole kernel apart and talks to you at extreme length, longer than I've been talking tonight even, about how the system's put together. You can get Linux Kernel Development. That's a book by Robert Love. He's also based in the Boston area. That's a great book as well. That's more of a kind of higher level book. Talks about development concepts. Kind of leaves the rest up to you to figure out. Linux Device Drivers concentrates on writing drivers for specific kinds of device. So I want to write a sound driver. I've already got my Linux up and running on this board, but I would like to support this proprietary CAN bus in my CAN. Probably never heard of it. No one has. It's a bus used in industrial automation. If I want to support that, I may need to write a driver for it, so I can read that book and write a driver for it. If you're working in the embedded space, doing some more interesting, funky stuff, then building embedded Linux systems, it's already out there. It's a good book as well. Okay. So once you've got all the kind of prerequisites in place, what do you do next? You need to bring up the system. What do I mean by bring it up? Well, I mean bring it up by its bootstraps, get it working, get it to do something for the first time. Okay? So we need a firmware, we need some BIOS, we need something that's going to run on my machine and get it to the point where I can even use a Linux kernel. Okay? This is useless when I turn it on. It doesn't even know how to talk to its memory properly. Okay? When I turn this on, it's got no caching support. It's not able to, it doesn't have any performance optimization. It has very, very little, minimal support, enough to load some code and run it, but not enough to really do anything interesting with Linux. So I have a piece of code. The reason I have a BIOS, the reason I have Linux BIOS, U-boot, Red boot, one of these things running. On a PC, I'll have a regular BIOS written by one of those companies you see when you turn your PC on. And the reason you have that is your machine does not know how to properly talk to its memory, how to properly take advantage of a lot of the fundamental features it has until after they've been set up. Yes, it can load some code and run it, but can't do very much until this piece of code has come in there first. This piece of code also may support more than just getting the memory working, getting caching support turned on, these kinds of things. It might also be a load of file from a compact flash card in this case, or it might be able to find a file on a network, something like this, and boot it, take a kernel from somewhere and run it. Or you might need an extra step in here on your PC. You guys already have seen Grub, Milo, some of these tools. They get called by the BIOS. They're sitting on your disk. They get executed. Their job is to then come in and run the kernel itself. No question. Good. You might have to port the firmware to your device. You might have to get this firmware up and running. So you get your tool chain in place. You get your debugging tools in place. So you need to make sure you've got GDB. You've got the different tools you're going to need to fix things when they go wrong. And you spend a lot of time hacking code. A lot of time. I mean, you're looking at, so going back to my MRI example or our NMR example, by the way, if you ever wonder why they use the term MRI and NMR, the reason is that people don't like the word nuclear. Okay, so we have MRI, which means exactly the same thing, but doesn't have the word nuclear in it. It's a lot more acceptable to people. That's why the term exists. Okay, so we have Linux running for our system. We want to get it up and running on our new kind of funky device. And when I started work on the previous project, we just had the hardware barely working. We had some problems with the memory. Every now and again we'd run some code and something completely different would happen because actually it was getting corrupted as it was being pulled in from the RAM. You have to worry about things like that. Normally you take it for granted that the memory in your machine is working. And we went probably within 2 weeks of getting the tools and getting a basic system in place. We were able to start having the Linux boot process come up, to start having messages coming out from our kernel saying, I'm trying to do this, oh, panic, something went wrong, and then you start sitting there going through endless hours of debugging cycles. And once you get to kernel build number 2000 and something, then you start to get somewhere. You're looking at thousands and thousands of rebuilds. But fortunately, we can cheat. I was going to say porting the Linux kernel by cheating, but I thought I probably shouldn't say that. Most systems are variants of existing ones. Okay? We don't tend to go out there and buy something that's so radically different from what we had before that it changes the world, despite what the marketing says. Okay, the marketing's going to tell you it's great, it changes everything. Well, it doesn't, it just adds the latest version of some device that you probably already had before. You probably already had a wireless chipset in your laptop. You got a new laptop, it had a new revision of that wireless chipset. Yes, it had some new capability, but it's still fundamentally a very similar device. So we can take the fact that systems tend to be based or related to existing ones for granted. We can copy the platform files in our kernel. We can go in there, we can say, okay, here are the support files necessary for this device here. In order to support this device here, which is similar, I simply make a few changes. I copy those files, I make a few changes. That's fine. That's exactly what we're supposed to do. That's how free and open source software works. Nothing wrong with doing that. And we add drivers for our custom devices. Things that we've made changes to, things that we've added that weren't there before, our actual innovation, we add that after we've got the basic system going. Okay, so I can, I'm aware time's getting on, I can go through an example in the next sort of 5 minutes of porting to a PowerPC processor and how that's done, or I can break now and take questions. Can we overrun by 5 minutes? Is that okay? All right. So I will go through a brief example of porting Linux to a new PowerPC platform. Okay, so you've got two directories here. You've got the include directory in your kernel source, and you've got the arch directory in your kernel source. Okay, and broadly speaking, what happens is you spend all your time worrying about files within the arch, your arch, and the corresponding include files for that particular architecture. So I'm working on a PowerPC processor. I'm modifying files in arch/ppc. In fact, now it's being renamed to PowerPC, but we'll ignore that. And I put some header files in there to kind of add constants and other things that I want to use. When the PowerPC system starts running, there's a standard defined function which every 32-bit PowerPC device, or in this case, this is a slightly different type of PowerPC device, but every single system is going to run this function called platform init when it starts up. Okay, it's going to do some other stuff, architecturally mandated stuff. It's going to get the memory system up and running properly, things like that are different for every architecture. Then it's going to run platform init. The job here for us as platform porters is to supply platform init and use it to educate the kernel about the arrangement of the devices in our machine. So we tell it about the networking devices we have. We tell it, okay, by the way, you've got a network chip at this address. On a desktop machine, we don't have to do these things. Sometimes in the embedded space, we do have to specifically tell Linux about even things like networking. Okay, but even if we're on a regular kind of machine, we've got a PCI bus, and Linux can figure out for itself all the rest of it. We still have to tell the kernel, okay, we have a PCI bus on this machine. We have some very basic components in our machine. We have to educate the kernel that they exist. We have to set up the kernel so it can do everything else. We have to set up we have to set up all the devices in our machine. We have to work around any known issues. Okay, there are lots of bugs in hardware. There are even more bugs when you take a hardware, particular architecture, you build a platform, you're going to make a couple of mistakes. You need to work around known issues. So you go through your errata documentation that tells you from your third-party suppliers that says, okay, if you try to do this, then this problem's going to happen, and the way to get around it is to modify your startup so that when your machine starts, you do this and this and this and this, and then hopefully that problem won't happen. Okay? So you have lots of kind of workarounds you have to apply early on. Okay? So you have some header files, put some constants in there, you define things like how fast your machine is running, where your memory lives, where different devices live. These addresses here are physical hardware addresses within my machine that we can use later to refer to specific hardwired locations. So back in my platform code, I have my platform init function that I'm implementing myself. It's called early on by the kernel to get the hardware up and running. It contains some interesting, it gets past some interesting information. When you come into this function, you are told about, in the case of PowerPC, you are given a board info structure that your firmware or your BIOS wants to tell you. It wants to tell you, this is the MAC address you should be using on this network device. This is the location of the boot image that the user has supplied. This is the location of the file system that the user would like you to use. Anything you might have set in your firmware or in your bootloader needs to get passed in. The location of the initial RAM disk. If you're using an init RD, one of these RAM disks that we use on modern systems, we boot the system by using a RAM disk. If you have one of those, you have to tell the kernel where it is. That's the job of the bootloader. The firmware, it tells it where that is. We want to save this information somewhere. If we have an initial RAM disk, we want to make it available. We want to produce lots of debugging output. At this point, we don't necessarily have support for a console, for a frame buffer, for anything that can actually output debugging information to a screen or other device. We have no way necessarily of communicating with the outside world. So to debug this, we might still be using our hardware debugger, right?
Or LEDs.
Or LEDs, yeah. And in fact, actually what you get really good at with when it comes to LEDs, you get really good at flash patterns, right? You get very good at, if it does 1, 2, 3, then I'm at this line, and and I'm sure some people have done little flash counters, you 2 LEDs, and it'll count the line number of the source code based on how many flashes. I'm sure people have done that kind of thing. But yeah, you have all kinds of horrible things to do. In the case of the port I was doing most recently, we actually I wrote a function that effectively output data to the serial port on the machine. It didn't matter that the machine didn't know that there was a serial port yet. There was no serial port driver loaded, but I wrote some code that effectively sort of forced those characters to get written out. No matter, it just wrote to a memory location, and I knew it was a serial port. The kernel didn't really understand what it was at that point, but I knew enough to be able to output something useful, at least know what line number I was in my source code when things went wrong. Platform init sets up all kinds of stuff. I have to tell the kernel how it can find out about interrupts. If you take your laptop, anyone who's got a Linux laptop, you type cat proc interrupts on there, you can see the interrupt numbers and what devices are assigned to which interrupts on your machine. You may have to educate the kernel about that, so you can do that. You have to tell the kernel about, how do I reset the machine? When the user types reboot, that's all very well. The machine's gone down, everything's shut down, sitting there. And how does the kernel tell the hardware, okay, that's great, I'm done, physically reset me now, okay? That might be different for different kinds of machine, okay? So, just an anecdote there, the Linux reboot process, in case you didn't know this, reboot in Linux actually uses a couple of system calls. It's implemented using this keying system because we don't want the kernel to ever think we're accidentally wanting to reboot, right? So when the user types reboot, the reboot command will send the kernel some magic numbers. They happen to be the birth dates of Linus's children, okay? So if you look through the commit logs, you'll see a few years back, there was a patch posted that said, we need to add a new reboot. We need to add a new line here. He had a new child, so he had to add a new key in there. So when you type reboot, one of those magic numbers gets sent to the kernel. It then starts going down through the reboot process. But when it gets to the end, it has to know how to tell the hardware, I'm done now. We have a command to do that. How do I set up time? How do I find out what the current time of day is? How do I, anything like this, how do I find how much memory I have in the machine? We have to be told somehow, so we set that up. Most platforms are very similar. They just have different memory layouts. You just have basically devices in different locations, different addresses in memory. You know, I have a network card in this machine. I have a network device in that machine. They're fundamentally very similar, but I might need to worry about a change in memory address and location of these things. Drivers are a different matter. I'm not going to get into that right now. Where possible, we use generic subsystems, PCI, USB, these things, so that I don't have to tell the kernel about the address of my networking chip. It's able to figure this out. If you have this machine here, you know, there may not be a PCI bus, so there's no point having a PCI network card on it. It's not going to find anything, there's no PCI bus, right? So I have to hard code it. I have to tell the kernel, this is where your network chip lives. But on a standard machine, with PCI, it's going to be able to figure this out for itself, so you won't have to tell it about that. Anyone who was wondering, you know, why is he talking about hard coding this? We all know that it's automatic. It's only automatic on your PC because you have standard buses into which you plug things, right? You plug your USB mouse in, you know, the kernel knows that there's a USB bus on the machine. It already knows that. Once it finds out about a new device, it's fine. But you have to tell it about these basic systems in the first place. And user-space device drivers we mentioned before. I think we're basically getting there. Building a complete system. System is more than a kernel. Kernel on its own is very, very useless. It doesn't do anything unless you actually run something. So we need a working distribution. We need to be able to handle software updates on our machine. Okay, did you want a web server? You know, generally you want to be able to do something. This device here runs the OpenWRT software, openwrt.org, and I expect that Linksys there probably does too. It's software, third-party written software for this device. This happened to run Linux in the first place. The vendor was obliged to release the code, so the community took that code and released a new distribution for this device. It runs a web server, it runs a whole bunch of things, but it also supports Wi-Fi networking, which is what it's designed to do. So, you know, you have to add in the things you actually want to give the functionality. Yeah.
I know BusyBox, but not
PTX disk? Yeah. Okay. So, so I'm just to get to that point. So you then want to put a distribution on your machine. You can probably go to a vendor. If it's a PC, you can just put a Linux distribution on it from wherever. If it's not a PC, if it's a more interesting device, you may need to get a hold of PTX disk, BusyBox, one of these utilities. They can help you to build up a usable software environment for your device. PTX disk effectively is a collection of scripts that will build up your bash shell, your init scripts, build up a very minimal distribution for your machine. BusyBox is a Swiss Army knife. It's a single program that provides the functionality of many others. PTX disk extends upon that. But basically, you download a bunch of stuff, you add it to your machine, you experiment. You know, a lot of this is just by experimentation. And just before I finish, I want to mention updates. It's very, very important whenever you build something that you handle software updates. If you've got a device like this one, with a compact flash card, you want to design it so that it can keep multiple copies, multiple known working configurations. Okay, so that when the user says, actually, that was a really bad update, there's a way of going back. It's good from your point of view as well, because you know, if you're Buffalo making these devices, you'd really like it if the user didn't have to return it whenever the power failed on an update. Okay, so what they tend to do is have a piece of code on here that's not modifiable, that can't be upgraded, that kind of starts the system up and running, a piece of firmware, if you like. Then they have the upgradable part, and they'll keep a spare copy, a known working configuration, so that if, when the system tries to start up, it for some reason fails, it has something else it can try. In the case of the project I was working on, we had 16 alternative configurations. So when the machine booted up, it could try 16 possible last known working configurations. I like to over-engineer things just a little bit, so we used to do that. Okay, so I already mentioned a few of these things. I'm also into hobbyist stuff. I actually only brought this is probably about 10% of the junk that's kicking around my apartment. I just moved here. There's a lot more stuff arriving. So maybe on one of the install days or something like that, I'll bring down a few more interesting and more expensive devices that I can keep an eye on, but we can play around with. So that's the end of the talk. And if anyone afterwards wants to come up here and try out one of these gadgets and get them hooked up and play around for a few minutes, then that's fine. Just before we go to questions, I will just mention, if you want to play around for yourself, this is called a Blackfin. This is from Analog Devices. Some of those guys are based here in Boston. And these are under $100 for a board you can buy, have at home. It comes with the tools you'd want, anything you need to get up and playing around with it. And if you're into electronics or anything like that, you've got plenty of options here to plug in anything that you want to attach to it. So it's a very cheap, very low cost device.
I just want to add that I was in the market for something like that a little while ago, and the keywords to look for is developer's kit.
Yeah.
Typically what you'll find is somebody is making a particular board or even just a chipset to be sold as an embedded product. They often have a version of the board that has some lights and switches on it and stuff like that, so you don't actually have to build a device around it to use it. Sometimes they'll also call it an evaluator board. And if you want to fool around with this kind of stuff and you don't want to deal with more hardware past the board, you could buy these evaluator boards, and they're usually relatively inexpensive compared to what you'd think for what you get, because it is almost a marketing tool. So I've seen them at Linux World. One vendor was selling them for $50, $60 with the documentation and the USB port, and with an 8-segment, 7-segment LED thing and switches and stuff like that.
What vendor was this?
The name escapes me. If I heard it, I would remember. But it was I think it's the only one left that's using the Z80 chip. I forgot which one. Zilog.
Yeah.
Yeah. Themselves, they had their own thing there.
I was going to say on the Zilog front, Zilog right now don't have. Do they have a device you can put Linux on now? I thought they.
I don't know that you can put Linux on that particular
they have
device.
the EZ80. I have one of those kits.
Yes. Yeah.
They're like $50, maybe $100.
Yeah.
But this is great because it's a very, very cheap system that can run Linux, has enough memory to do something useful, has some flash so you can flash it, has networking. Okay, that's all you need.
For another $100 or so, you can upgrade to the Easy Kit. So that's a stamp. You can get the Easy Kit, which also has audio and it has a bunch of other stuff. It also has some proprietary stuff that ties into ADI's tools, but the audio alone.
I blogged about ADI's tools a while back. Yeah. Read my blog. It's a very interesting story there. I won't go into it now. But AD generally have done a very good job with this stuff, and I'm not trying to promote them. I don't get paid to promote them. I did get this free, but that's a different story. But these are very, very cool.
It does have a really good UC Linux team and very good documentation.
But no FPUs on the back ends.
No, but it is a 500 megahertz chip, so I don't care if it's emulating all my floating point. It's great for running a web server.
Yeah, one other nice option is to get one of the PDAs that runs Linux, like the Sharp Zorus. You could buy those on eBay right now, like the original models, like mine, the 5500, for like $100 these days. So not only do you have an embedded Linux thing, but you've got video hooked up to it and serial ports hooked up to it.
I actually have one. I lent it to somebody.
Right.
They have a tendency, because they're very cool, they have a tendency of never coming back, but they are very, very cool little gadgets. Yeah. They also have a broken firmware updater on the Zorus, so that
Yes.
when you have to press the magic key combination when you turn it on with a compact flash card in, that happens to have the right image on it, but it will only read through that. It doesn't understand the file system properly, so if you have a slightly damaged compact flash card, you waste a Sunday afternoon custom editing the FAT so that you can make it work. I've done that, and that's horrible. So
Yeah, I've never heard of that problem, but there is,
don't use broken compact flash cards.
Yeah,
Use a working.
there's at least 5 different open source Linux distributions for the Zorus in particular. If you do come back and you want me to bring mine, I will. I think Jabra has one also.
So would anybody, just before we finish then, would anybody like another time to have a kind of, it's going to have to be a smaller session, or we're going to have to just kind of, you know, double up and share or whatever, but have a hands-on session where we get some hardware in, especially if a few of us have sort of some PDAs that are very similar that we can share. That might be a cool session to
Yes. I'd be
And we can
interested
do
in
that also as part of an install fest.
Yeah,
Because we have the 2 rooms downstairs and it's fewer people.
yes. Okay. Thank you.
Thank you very much.